Hi, welcome back. So today we're going to discuss about um, work energy theorem. Okay, so our objectives for this topic is that we should be able to define the kinetic energy and potential energy later, and you should be able to apply the work energy theorem to determine the work done on an object and apply the work energy theorem to calculate the displacement and velocity of a moving body as well as the force acting on it. So first is we are going to define these types of energy, the the kinetic energy and potential energy. So first let's define kinetic energy. It's actually the energy that an object possesses due to its motion. Again, it is a scalar quantity and depends only on two factors, that is the mass of the object and its velocity. So the formula for this is you have ke is equal to 1 half mv squared, where your v is the velocity and your m is the mass of the object. So you'll have your m is the mass and v is the magnitude of the velocity. Okay, so take note that this is a scalar quantity, so we do not consider the direction. We do not consider a direction in this in calculating this one because this is a scalar quantity. Okay, so we have an example here. So calculate the kinetic energy of the student walking at 0.15 meters per second with a mass of 60 kilogram. So you're just going to use the formula ke will be equal to 1 half mv squared. So this will be equal to 1 half times the mass multiplied by the um, magnitude of the velocity, which is 0.15 meters per second, and this is squared. So the ke will be equal to, okay, so that is 1 half times 60 times 0.15 squared. So that is 0.675 joules. So as simple as this. Okay, so now we proceed with the potential energy. Potential energy is defined as the energy stored in an object due to its position or configuration. So it is a form of mechanical energy and can be converted into kinetic energy when the object moves. So the most common type of potential energy is the GPE, or what we call the gravitational potential energy. So that is GPE. So sometimes it is written with this in the books. Okay, so this GPE is actually equal to mgh. Okay, so where your m is again the mass and g is the gravitational value, which is 9.81 meter per second squared because we're here at Earth, and the h there is actually the height. Okay, so again, our gravitational potential energy is only dependent on the mass and the height. Okay, so suppose this is our situation and this is our height h. Suppose we have this ball. So this is actually a ball, a falling ball. And with, let us say, with a mass m. Okay, and the height, let us say, this is 2 meters, and the m is, let us say, 0.3 kilogram. So if if we're going to calculate the potential energy of the ball, so we can write that as GPE ball will be equal to mgh, so this will be equal to 0.3 kilogram, and then it will be multiplied with the g value 9.81 meter per second squared, and the height value, which is 2 meters. So your GPE here will be equal to zero point 0.3 times 9.81 times 2. So this is 5.896. Okay, let me check. That is 0.3 times 9.81 times 2. Okay, 5.886. So this is 5.886 joules. Okay, so let's follow here two significant figure values. Maybe I'll change this to 2.0 meter. This is 2.0 meters, and the mass will be 0.30. Okay, so we can express this answer now as 5.9 joules, following two significant figures. So that is how we calculate the potential energy and the kinetic energy of a body. Okay, so now we're going to define the work energy theorem. So the work energy theorem states that the total work done on an object is equal to the change in its kinetic energy. Okay, so our situation here is like this. Suppose we have a moving body here, regardless of the force that's being applied to it, as long as it is seen at this time that it has this position at this certain position. So let's call this as our x-axis, and at a certain position xi, and then since it is moving with a velocity at this time, so it's given with a velocity, initial velocity vi, and then this is ti, and suppose that it's here at position xf with a time t final, and of course if there's an observer here, uh, that observer is going to record the value of its velocity here as vf. Okay, so the work energy theorem in this case, so it states that the work done on this object of mass m is equal to its change of kinetic energy. So we can write that as the work is equal to the change in kinetic energy. So previously um, we have defined that earlier that the kinetic energy is equal to 1 half mv squared. So you have, if you expand that one, this is work is equal to ke final minus ke initial, or you can just write that as, okay, let me put that here. You have work is equal to 1 half mvf squared minus 1 half mvi squared. Okay, so we can factor out m, 1 half m, then you could have this 1 half m vf squared minus vi squared. Okay, so this states that the work done on moving this object, okay, regardless of the force, is equal to its change in kinetic energy. So we can just calculate the work done here. We don't need the displacement. We don't need the force. We just need its value for the velocities, as we can see from the formula here. Okay. Okay. So how was that formula earlier was actually derived? So you have that the work is equal to change in kinetic energy. Okay, so we go back to the basic definition of work. That is, work is equal to force times distance. Okay, so what? According to Newton's law, we can still expand this as um, ma times d. Okay, so because of Newton's law, that is F is equal to ma. So following that, you have work is equal to the mass times acceleration times d. And previously from our kinematics, um, you can actually calculate the acceleration of the body. That is um, xf minus xi is equal to vf squared minus vi squared over 2a. Okay, so if we're going to derive, oh, no, not derive, but take note that d here in our equation is just actually the displacement, and this is also a displacement, so this is equal to d. So we're going to substitute this quantity here to our equation here. So you will have work is equal to ma, that will be multiplied with vf squared minus vi squared over 2a. So notice that our a here will just cancel, and then finally we have 1/2 m times you have vf squared minus vi squared, and you will have 1/2 m vf squared minus 1/2 m vi squared. So this is just ke final minus ke initial, or just simply change in the kinetic energy. Okay, so that is the formulation of this work work energy theorem, that is going in one dimension along x-axis, um, that the work done is actually equal to the change of the kinetic energy of the body. Okay, so now let's apply our learnings earlier to this problem. So it states that a 2 kilogram cart is pushed along a horizontal surface by a constant force of 10 Newton. So the car starts from rest and moves a distance of 5 meters. Okay, so in order to solve this problem, it is my advice that we write the whole formula for the work. That is, this is equal to force times distance, and that is still equal to mass times acceleration times the distance, which is also equal to the change in kinetic energy. So in this case, if write it like this, then we can just look for the relationships, right? Here we can derive that, that is by transitive property of mathematics. We can have ft is equal to delta ke. So we can do it like that. Okay. So letter A, calculate the work done on the cart by the applied force. Okay, so this is actually easy. So we're going to use the force times distance here, because we have a known force that is 10 Newton and the displacement t, which is 5 meters. So simply work will be equal to force times the distance, which is equal to 10 Newton times 5 meters, which is 50 joules. So again, don't forget about the units. And letter B, determine the final kinetic energy of the cart after it has moved 5 meters. Okay, so from work energy theorem, work will be equal to the change in kinetic energy, okay, which is equal to KE final minus KE initial. Okay, so in our problem, it states that it's just pushed, okay? So meaning um, the cart actually started from rest. So if we expand this one, this will become 1/2 mv squared minus 1/2 m vi squared. So since it started at rest, our initial velocity here will be 0. So you will be left with 1/2 mvs squared, which is the KE final. So from the relationship, your KE final will just be equal to the work, which is just still 50 joules. Okay, so letter C, find the final velocity of the cart after moving that distance. Okay, so we need to find the final velocity of the cart when it has already 50 joules. Okay, so we already know that when it moved 5 meters, it already possesses a 50 joules of kinetic energy. So you can just write here KE final is equal to 50 joules, which is, you can expand that to 1/2 mvs squared, which is equal to 50 joules. So from here, you can just solve that. Um, that would become Vf squared is equal to 2 times 50 joules divided by m, and take the square root both sides. You will have Vf is equal to square root of 2 times 50 joules over m. Okay, so now we're going to substitute the value of the m so that we can get the value of the velocity. Okay, so the formula for that was Vf is equal to square root of 2 times 50 joules divided by m. Okay, that is whole square root. So this will be square root of 2 times 50 joules over the mass, that is 2 kilogram. Can then plug that to the calculator. That will just become square root of 50, and the result will be 7.07. So 7.07, the unit will be meter per second. Okay, so I will express my answer into two significant figures. Vf will be equal to 7.1 meter per second. So this will be the answer to these problems. Okay, so another question would arise. What if our motion is not actually in the x-axis? So what if our motion is actually described like a falling ball? So it's in the y-axis. So how do we calculate the work done on that? So it is clear that when an object is in the air, its motion is greatly its motion is only affected by gravity. That is, if we consider the absence of air resistance. Okay, so now let's consider again a falling ball. Okay, and let's actually draw the ground here. Now, of course, this ball has some certain height from the ground. Okay, so just like as I have taught you in the projectile motion, um, we always consider that the start of our motion is actually our origin. So in this part here, this will be our y initial that is equal to 0. And this ball will fall, let us say here, that is, let us say this will be y2, and finally it will reach the ground at some certain height that is y3. And take note that our yi here is actually 0, so all values of y below that 0 will be negative values. Okay, so now how do we calculate the work done on this ball? Okay, so let us say that the height here is 10 meters and the mass of the ball is 1 kilogram. So that is a heavy ball. Okay, so we always go back to the definition of the work. So work is equal to force times distance, and when this ball is actually in the air, the only force that would act on it is the weight, the weight of the ball. Okay, that is in absence of air resistance. So we can just identify that F here will be equal to the weight. So if we expand our formula, the work done here is just equal to weight times D, which is equal to mg t. Okay, so this d here is actually our displacement. Okay, so this is a familiar formula that is from our potential energy, right? So the potential energy is equal to mgh. Okay, so if we change our d here from our variable here, that is h, which is the displacement of the ball from the ground, then we will get the work will be equal to mgh, which is equal to its potential energy. Okay, so now the question is, what if we want to find a specific work done by the gravity on the ball at certain heights, that is, let us say at y initial and up to y2. Okay, so we will substitute that here. So work will be equal to mg, and the displacement there will be from yi minus y2. Okay, so let's take a general form of that. Let us say yf. So if we distribute mg, this will become mg yi minus mg yf. So this term here and this term here, we can write that as pe initial minus pe final. Okay, so we can rewrite this as negative of pe final minus pe initial, and finally we can write that the work done on the falling ball will be the negative of the change in its potential energy. So you have here the relationship, the work done and the energy, the potential energy. Still it follows the work energy theorem. Okay, so let's have an example. We will go with the example later. So take note that in our x in our motion along x, we have derived that the work is equal to the change in kinetic energy. And in our motion in y-axis, we have also derived that the work is equal to the negative change of potential energy. Okay, so if we're going to write the equation for this, this will become work is equal to change in kinetic energy, which is also equal to negative change in potential energy. So from this, we can conclude that the change, okay, so from this we can have the equation change in kinetic energy is equal to negative change in potential energy. If we expand, this is KE final minus KE initial is equal to negative PE final minus PE initial. So this will become KE final minus KE initial is equal to PE initial minus PE final. Now I'm going to group the quantities with the final quantities and the initial quantities. So I have here KE final plus PE final is equal to KE initial plus PE initial. Okay, so I think it's more beautiful to write this as KE initial plus PE initial is equal to KE final plus PE final. Okay, so this equation right here, okay, is actually what we call the conservation of mechanical energy equation. Okay, so sometimes it's just called mechanical energy equation. Okay, so this is only valid. So this is only valid if we don't consider um, air resistance and friction. Okay, so these forces here, air resistance and friction, are examples of what we call non-conservative forces. Meaning, this equation here is only valid if we don't consider these non-conservative forces, which are air resistance and friction. Okay, so we're going to proceed now to the example. Okay, so we have an example here. A 2 kilogram ball is dropped from a height of 10 meters. Then, ignoring air resistance, what is the work done by gravity as the ball falls? And then the velocity of the ball just before it hits the ground using the work energy theorem. So it's always the ball. So the very classic example. Okay, so this is our ball. And that's it. So let's say the brand of this ball is Spalding. Okay. And the height is actually 10 meters. This is the ground. So we are asked how much is the work done and the velocity at the ground. So let us say that is the velocity final. Okay, so we're going to apply the energy conservation mechanical energy equation, okay, or the energy conservation formula. So we will label this our initial point, and at the ground will be our final point. So writing our conservation energy conservation formula, we will have PEI. This is equal to KE final plus PE final. Okay, now so since the ball is just dropped, meaning its initial velocity is 0, and that would mean that our initial kinetic energy will be as well 0. Okay, so when this ball finally reaches the ground, so that will have our h is equal to 0, so meaning our y final will be equal to 0. Okay, so um, okay, so that's it. So you'll have um, that is based on my reference point. So I will have here that the PE final will be 0. So I will be left with um, PEI is equal to KEF. Okay, so I will expand this one. This will be mg y initial, which is equal to 1/2 mvf squared, and um, what I will do here is find the expression for vf. So I'll have vf will be equal to um, square root of 2g yi. Okay, so you might have a confusion of, is my yi 0, is my yi 10? Okay, so from earlier of what I have derived, so that is for my derivation purposes only. So I always take into consideration that the start of my motion will have my xi and yi, or my origin. Okay, and the what? Okay, no, I've said it in a different way. I always take into consideration that in the initial part of motion, that is where my yi will have some certain value, and then your yf here will become 0. Okay, so my yi here is not 0, okay, because I will not consider this now as my um, xi equals 0 and yi equals 0. I will not consider that now. Okay, so following this one, this will be square root of 2 times 9.81 meter per second squared times the 10 meters. So the velocity of the ball when it reaches this part here will be equal to that is 14 meter per second. Now, what is the work done by the gravity? So the work done by the gravity, okay, so I will write that in this part. So the work done by gravity will be equal to mgy. So this is actually mgh. Okay, we can write that as mgh. Which is equal to 2 kilograms times you have 9.81 meter per second squared times the 10 meters height. So the work done by gravity will be equal to times 10. So this is 196 joules. Okay, so this will be positive because the direction of our force is actually now going with the direction of our displacement. Okay, so when your force is in the direction of the displacement, the work will be positive. Okay, so actually we can apply the formula earlier. That was work. Let's label it with work due to gravity is equal to the negative change in its potential energy. Now you have work due to gravity will become negative of mg, this is PE final minus PE initial, or I can just write that as negative mg yf minus mg yi. Okay, so if I'm going to um, this is my height here and this is the ground. If I'm going to let this as my yi equals 0, then my y final here will be equal to negative 10 meters. Okay, so I have my yi here as 0, so this here will be 0. So I will be left with negative mg yf. So if I substitute that, this will be negative 2.0 kilograms times 9.81 meter per second squared times negative 10 meters. So the work due to gravity here will be equal to positive 196 joules. Okay, so because again, same reasoning, um, our derivation earlier was actually to take into account um, whether the displacement goes down or goes up. Okay, so in here, our vector for weight is here going down, and our displacement is also going down. So we should expect that the work done will be positive. So it's a different case again if we actually trying to lift this ball. So the work done will be negative because um, the work done there by the gravity will be negative because we are trying to lift the ball and then the force vector of weight is always going down. So the displacement and the weight vector are in opposite direction. That's why we'll have a negative value. That is if we are trying to lift the ball. But if we release it and there's no other applied forces on it, then the work done will be positive. Okay, so that will be um, an application of the work energy theorem in this case. So we'll have another example. Okay, so let's consider this example here. We're going to apply the energy conservation formula. We're going to find the kinetic energy at point B. What is your KEB and what is your KEC, as well as the different velocities VB and velocity at point C. So let's start at finding the kinetic energy at point B. Okay, so here we can write here KE A plus PE, PEA. And here we can write here KEB plus PEB. So according to our formula earlier, we can just equate that. You have KEA plus PEA is equal to KEB plus PEB. Now, we're going to identify what values are actually zero. And since at point A, it's the start of our motion, so it just slides there. So, meaning its initial velocity VA, okay, VA is equal to 0, meaning our kinetic energy at point A is 0. So, we will be left with the expression here, PEA is equal to KEB plus PEB. So, from here, we can already derive the KEB. That is KEB is equal to PEA minus PEB. Now, if we're going to expand, that will be equal to mg YA minus mg YB. Or finally, you can just have mg YA minus YB. That will be the value of your kinetic energy at point B. So the kinetic energy at point B will be equal to the mass 3 kilograms times the gravitational value 9.81 meter per second squared multiplied by the difference of the heights A and B. That is 15 meters minus 10 meters. So if we're going to plug in that in the calculator, we should have that is 3 times 9.81 times 5. So that should be approximately 147 joules. So this is 147 joules. Okay, so um, for the velocity at point B, so we can just expand this expression here. You'll have 1 half mvb squared is equal to mg YA minus mg YB. So the m here is common, so we can just cancel that out. So you'll have VB squared is equal to 2 times that is 2G. You'll have YA minus YB, or your VB will be equal to square root of 2G YA minus YB. So this will be equal to square root of 2 times 9.8. So that will be 9.8 meter per second squared, and that is multiplied by the difference YA minus YB, that is 5 meters, and you will get the VB, which is equal to that is square root of 2 times 9 point, okay, let's use 9.81 here. So 9.81 times 5, so this is 9.90 or 9.9 meters per second. Okay, okay, so now how about at point C? How will we calculate the KE at point C and the velocity at point C? Okay, so I think you can try that on your own. And just a question, um, um, try, not a question, but just an extra, try getting the sum of energies at point A, point B, and point C. So what do you mean by that? You're going to sum the kinetic energy and the potential energy at point A and get the value, they get that value, and also for B and C, and then um, try to compare. No, I will just tell you the answer. They will be actually um, the same. Okay, they should have the same value or close values because of our approximations. So and what I want you to do is, why is that? Okay, so you should have a reasoning for that, because sometimes um, that will pop out in the quizzes or the conceptual essays that should be able to explain why do we get that value. Okay, so that's all for this tutorial. So thanks for watching.